To determine if a vector field is source-free, we first need to define the term source-free. We will start with the definition of a conservative vector field, since the relation between circulation and a conservative field is the same as the relation between flux and a source-free field. Note that for a simply connected domain, the flux around any curve must be zero. On a simply connected domain, a source-free field can be defined in multiple equivalent ways. If we let F be the vector field PQ, we have the following definitions. The first possible definition states that the flux across any closed surface is zero. The second possible definition states that the flux across any closed curves are equal. The third possible definition states that the vector field F has a stream function g. The fourth possible definition is P sub x plus Q sub y equals 0. For this example, we'll try to verify that vector field f of xy equals negative yx is source-free. To do this, first we must check that the constraints are met. First we must check if the domain of f is in R2, which it is, and second, that the domain is simply connected, which it is. In this example, we will use the fourth definition, P sub x plus Q sub y equals 0, to show that the field is source-free. Using this definition, we will take the derivative of P with respect to x to find P sub x. This gives us P sub x equals 0. Then we will take the derivative of Q with respect to y to find Q sub y. This gives us Q sub y equals 0. Substituting the values for P sub x and Q sub y into the definition results in the following equation, which is equal to 0. Since P sub x plus Q sub y equals 0 matches the definition of a source-free field, then the vector field F must be source-free. Now let us find a stream function for the vector field f of xy equals negative yx. For the given field, we must find g sub y and g sub x. Note that g sub y is the x component, and g sub x is the negative of the y component. Therefore, g sub y is equal to negative y, and g sub x is equal to negative x. Since the components of field f are the derivatives of the stream function g, the function g is made of the integrals of the components of f. So we have the integral of g sub y dy plus the integral of g sub x dx. Integrating g sub y with respect to y gives negative y squared over 2, and integrating g sub x with respect to x gives negative x squared over 2 plus c. After letting c equal 0, the equation for g simplifies to negative y squared over 2 plus negative x squared over 2. This is the stream function for the vector field f. We can confirm that we have found an appropriate stream function by taking the derivative with respect to y and comparing it with p, the x component of f, and then by taking the negative of the derivative with respect to x and comparing it with q, the y component of f.